Hi everyone. I'm going to be giving a talk on derived deformation theory following Galatius and Venkatesh's paper, Derived Galois deformation rings. This presentation is part of the Columbia Student Number Theory seminar. I'm not a student at Columbia, but I'm an associate professor at SUNY Old Westbury, and I'm just interested in actually changing my field and starting to learn number theory. Disclaimer. Nothing in this document is original, except for the mistakes. I have also liberally copied verbatim some sentences and paragraphs from Galatius and Venkatesh and a few other sources, and only sometimes give attribution. I'm not an expert, and my understanding of the material has large gaps, and I have made these slides ready to just help me learn the material. Please let me know if you have any questions, comments, or corrections, and I've given my email address there. Okay, so here's the outline of the talk. I'm going to begin by, after this, some technical statements that are the goals of the talk, then a brief motivation for derived algebraic geometry, before we get into the technical definitions of simplicial sets, simplicial commutative rings. That's from Galatius and Venkatesh, section 1, and it's been like a few weeks since we've talked about homotopy theory, so I thought I'd review some of that. Then I wanted to give some examples of the types of functors that will eventually be of interest in the paper. For example, the derived Galois deformation functor. Then I'll go to covering homotopy colimits and limits. Those are in the appendix to Galatius and Venkatesh. Then I'll review representable and pro-representable functors in sections 2 and 3 of Galatius and Venkatesh. And then the main topic, I guess, is a tangent complex of a certain type of functor, and that's in section 4 of Galatius and Venkatesh. That will involve introducing the notion of spectra, Dole-Kahn correspondence, and then finally I'll end with the statement of Lurie's derived Schlesinger theorem. So I want to begin by stating the technical form of the statements that I want to explain in this talk. So there's 3. So the first one is, let K be a field, a formally cohesive functor, and I'll explain what that is during the talk, from Artin simplicial commutative rings to simplicial sets, has a tangent complex of K vector spaces, and it's possibly unbounded in both directions, and it's going to satisfy some conditions that we'll spell out later. So the majority of the talk will be developing the tools needed to explain how to define this tangent complex that's associated to this functor f. And unfortunately, the strategy, there's not a direct definition. And so the strategy Galatius and Venkatesh use is to go through homotopy via something called HK modulo spectrum. So again, we start with the cohesive functor f, then we're going to define basically a sequence of simplicial sets fairly easily by evaluating this functor f at various Artin rings. And then there's also something called the Dole-Kahn correspondence, which is an equivalence of categories between bounded chain complexes and simplicial simplicial K modules. And that goes this way, and then the idea is to take the inverse of it, and that's how you get your tangent complex. And then finally, what can the tangent complex tell us? One thing it can tell us is if a functor is pro-representable or not, and this is Lurie's derived Schlesinger theorem. It says that if the tangent complex is what's called co-connective, in other words, the homology groups of the complex vanish in positive degree, then your functor is representable. So before getting into the technical details, let's give somewhat of an informal overview or motivation for derived algebraic geometry, and specifically the question of why bother considering functors from simplicial commutative rings to simplicial sets. And I'll follow a nice overview given in what is article, what is a derived stack, in the notices by Gabriele Vazzosi. So first fix a base commutative ring, K, for example, and let com_alg denote the category of K algebras. And in classical algebraic geometry, and by classical I mean Grothendieck style 1960s, not Italian school 1900s, there are two approaches to defining a scheme over K, and both are useful in their own ways. So the first is we can think of a scheme as a ring space. That is a pair X along with a sheaf of rings OX. So X is a topological space, and OX is a sheaf of rings on X. And then plus some conditions. In other words, we have like a cover by local models given by spec A and its sheaf of rings for some commutative K algebra A. So that's the first way. And the second way to think of a scheme is as a functor of points. So it's a functor from the category of K algebras to sets, and maybe with some conditions. And if you have a scheme X that you have as ring space, then the associate functor, often denoted H sub X, is its functor of points, given by this. Now, as a remark, not all functors from commutative K algebras to sets are isomorphic to H sub X for some scheme X. Those functors that are said to be representable by a scheme. Now, the functor of points approach is frequently used to define moduli problems. A moduli problem is basically a functor from K algebras to sets that assigns to a K algebra A a set of objects over A modulo isomorphisms. And then many such functors are not representable by a scheme, and that's usually due to non-trivial automorphisms of objects. So instead, we keep track of the automorphisms by considering the functors that assign to a K algebra A the objects we're interested in, together with isomorphisms between two objects. And such a functor takes values in categories, namely the objects of the category are the objects we want to study, and the morphisms are the isomorphisms between objects. A category in which every morphism is an isomorphism is also known as a groupoid. And this gives rise to the notion of a pre-stack, and if it behaves like a sheaf, some Grothendieck topology on the category of K algebras, it's called a stack. And then this leads to something called higher stacks. Often we want to classify objects for which the natural notion of equivalence is weaker than isomorphism. For example, for chain complexes of A modules for some ring A, the natural notion of equivalence is a zigzag of quasi-isomorphisms. In such cases, it's natural to once again enlarge the target category and consider functors from K algebras to simplicial sets. Or topological spaces. A stack can be viewed as a higher stack by taking the nerve of a groupoid. So our stack is valued in groupoids. Take the nerve, we get a simplicial set. The nerve again is just the n simplices are given by n composable maps. So Vazzosi article gives a nice diagram summarizing the situation we discussed so far. We started with schemes, then we went to stacks, then we went to higher stacks, each time enlarging the target categories of our functor. And Vazozzi says that, and here's a direct quote, the main point of derived algebraic geometry is to enlarge also the source category, i.e. to replace commutative algebras with a more flexible notion of commutative rings, serving as derived rings. And so here's a picture I stole from Vazozzi's article. We're going to replace this category of k-algebras by derived k-algebras. And it turns out that there's a few ways to model derived k-algebras or derived commutative algebras. And one way is simplicial commutative k-algebras, or if you're in characteristic 0, the category of commutative differential graded k-algebras. Why bother doing this? Well, there's many reasons. Derived algebraic geometry has quite a few applications, if you will. And Vazozzi's article focuses on two classical geometric questions. So one is considering derived intersections, and the second is deformation theory. Both of them relate to our paper, to the Galatius and Venkatesh paper, and so I wanted to say a little bit about them. So the first one is derived intersections. And what does that mean? Well, counting intersection multiplicity correctly has a long history, perhaps dating back to the number of roots of a quadratic polynomial. Well, is it 2 or is it 1? So there are various approaches in classical intersection theory to deal with non-transverse intersections, for example, moving lemmas, deformation to the normal cone, and so on. And so, for example, let V be a complex, smooth, projective variety, thought of as an ambient variety, and let X and Y be two possibly singular subvarieties whose dimensions add up to the dimension of the ambient space V, and such that X intersect Y is zero-dimensional. And of course we want to count how many points does X intersection Y have, and Serre's intersection multiplicity formula says that the intersection multiplicity at a specific point P is given by this sum of the dimensions of some Tor groups. And okay, well then the Tor groups can be computed in theory anyways by taking a projective resolution of one of the factors in the category of modules over your ambient space, tensoring this complex by the other ring, and then taking cohomology groups of the result. And it turns out it's possible to choose a resolution of OXP by a commutative differential graded OVP algebra, a CDGA for short, and tensoring the resolution with your other ring gives a complex that's denoted like so, sometimes called the derived tensor product, and we view this as a commutative differential graded algebra. And then there's a famous fact that if we are in a characteristic 0 situation, CDGAs are equivalent to simplicial commutative rings, and specifically there's a Killen equivalence between appropriate model structures. So the idea is to think of these as the basic objects of derived algebraic geometry and work with them. These objects contain some intersection theoretic information. Okay, so how does this apply to Galatius and Venkatesh and their Galois representations? They mentioned this in the introduction. So let V be the space, the moduli space of all p-adic representations of the local Galois field, or local Galois group. Let X be the moduli space of geometric p-adic representations, and Y be the moduli space of p-adic representations of the global field. And a quote from Galatius and Venkatesh is that it's unsurprising that a derived version of Mazur's Galois deformation ring should play a role because the intersection of x and y in general is not transverse. Okay, so then the second topic where derived algebraic geometry plays some role is something from the 60s and 70s called the cotangent complex. And what is that? Well, for K algebra A, we can find a resolution of A by simplicial commutative K algebras P such that at each level, P sub n, it's a polynomial K algebra. So for example, P sub 0 could be a huge polynomial ring K adjoin all the elements of A. Of course, typically there's much smaller choices, and P1 can be the polynomial K algebra on P0 and so on. And then consider the simplicial module of Kähler differentials. And then we can turn the simplicial module into a chain complex by taking the differentials to be the alternating sum of the face maps. And then switching to cohomologically indexing gives the cotangent complex of A over K. And well, what does this do for us? Well, classical deformation theory studies only a small two-term truncation of this complex, giving rise to this, the tangent and obstruction spaces, also the Kähler differentials and the XL com functors. In derived algebraic geometry, the full cotangent complex is studied, and this is related to Andrei Killing cohomology of rings and so on. And this will come up later in the talk, actually. Okay, so that finishes the sort of brief overview of derived algebraic geometry. Let's now start with some more technical stuff. Let's see, and this is in Galatius and Venkatesh. So since it's been a few weeks since we talked about simplicial sets and so on, let's review what's going on. So let delta be the simplex category. Its objects are indexed by the non-negative integers, and well, this is the object, and the maps are non-decreasing functions. So the category of simplicial sets is functors from delta op to sets. And so a simplicial set is just a sequence of sets x0, x1, and so on, then with a bunch of maps between them, generated essentially by the face and degeneracy maps. Okay, and then we equip the category of simplicial sets with what's called the standard or Killen model category structure, in which the fibrations are the Kant fibrations. Every horn can be filled in. A horn is kind of like the inclusion of a simplex where you omit a face to the full n simplex. Okay, so then the weak equivalences are mapped to induce isomorphisms on homotopy groups of the corresponding geometric realizations. And cofibrations have the left lifting property with respect to trivial fibrations, trivial being something that's a weak equivalence. Okay. One thing that's going to be used throughout this talk is that the category of simplicial sets is enriched over itself. What does that mean? Well, for two simplicial sets x and y, the Hom between x and y is not just a set, but a simplicial set. And here are what the n simplices are. This given by this formula. And then as an example, a one simplex between x and y is, you can think of that as a homotopy between the two maps f0 and f1 that are the restrictions of the delta 1 to its two endpoints. And then following Galatius and Venkatesh, we'll drop the underline on the Hom, and so always regard Hom x comma y as a simplicial set. And so for example, this gives us a functor Hom x comma blank from simplicial sets to simplicial sets. This will be an example of a representable functor, essentially. Okay. Now to simplicial commutative rings. Well, it's you can think of it as simplicial objects in the category of commutative rings, but okay, fine. We're going to enrich it in simplicial sets as follows. The Hom between two simplicial commutative rings R and S is a subsimplicial set consisting of level-wise ring homomorphisms. In other words, Rn to Sn is a ring homomorphism at each level n. Okay, and then the category of simplicial commutative rings is a model category. The fibrations and weak equivalences are those from the underlying simplicial sets, and the cofibrations are then maps in simplicial commutative rings that satisfy the left-lifting property with respect to trivial fibrations. All right, then let's recall the notion of an Artin local simplicial ring. So let K be a field, and in Galatius and Venkatesh it's usually a finite field, but right now we probably don't need that assumption. And consider the field K will be considered as a discrete simplicial ring. Art sub K is the full subcategory of simplicial commutative rings. The subscript K here means the rings have a map to K. That's part of the data of an object in SCR over K, such that, well, first condition is a discrete ring of pi 0, 0, pi naught of R is an Artin local ring in the ordinary sense with residue field K. And the second condition is the associated graded ring is finitely generated as a module over pi 0. And in particular, it's going to vanish if n is sufficiently large. Now, Art K is too small to be a model category as it doesn't have even an initial object, but we can study its homotopy theory via its inclusion into simplicial commutative rings. And so, for example, when we say that R, an Artin simplicial ring, is cofibrant, that means it's cofibrant as considered in the category of simplicial commutative rings. Okay, so before diving into sections 2 and 3 of Galatius and Venkatesh, which talk about functors, let's give some examples of such functors from the category of Artin simplicial rings to simplicial sets. So, one example of such functor is it came up before, it was Hom from R to something for a fixed ring R, and that's what's called a representable functor. And we want typically R to be cofibrant so that this functor is homotopy invariant. Okay, then a slight generalization of that is pro-representable functors, and that's where you have a pro-object of R, and then the associated functor is the colon. Then another example of a functor is a terminal functor. In other words, give me any ring A, and I just give you back the simplicial set that's basically a point. And this will not be representable for a field of characters of P, but it will be pro-representable. And I'll explain why later, but okay. And then finally, another example is if you give me a Artin ring A, I take the kernel and I believe I should have simplicial sets here. Okay, so then you get a simplicial K module, actually. Okay, so once we have some basic functors, we can cook up some new functors. If you have a diagram like so, then you can form what's called a homotopy pullback by this formula here, and I'll explain what homotopy pullback is later on. And a specific example of this pullback construction is the loop space functor. That's the homotopy pullback of that. Okay, now the real example in the Galatius and Venkatesh paper is the derived Galois deformation functor. And, well, okay, so we fix a prime P and a finite field K of characteristic P. Let S be a set of primes containing P. And then we fix the Galois representation. It's one of these mod P representations in one of the senses of the term, because the coefficient field K is of characteristic P. And so a natural question is if it can be lifted, if this representation can be lifted to a Galois representations with coefficients in a p-adic field like the width vectors over K. So Mazur initiated the study of the underived deformation theory of rho, that is functors from discrete Artin K-algebras. So those are what's called ordinary, an ordinary Artin K-algebra to sets. And he showed that under certain hypotheses, various deformation functors associated to rho were pro-representable by discrete Artin local rings. And he did this by checking that the Schlesinger conditions were satisfied. Now, analogously, where Galatius and Venkatesh are going to consider derived deformation functors, and so those are functors from Artin simplicial local rings to simplicial sets, and their definition, unfortunately, is slightly involved. So I'm not going to actually give them in this talk. They're actually supposed to be the topic of the next talk. But informally speaking, what Galatius and Venkatesh say is the functor sends an Artin simplicial ring A to a simplicial set of conjugacy classes of deformations of rho to A. So again, the coefficients of rho are in K, and A has a map to K, and so we're kind of deforming the coefficients to A. That's a little bit of a naive or informal description. Anyway, Galatius and Venkatesh showed that some of these derived deformation functors are pro-representable using Lurie's derived Schlesinger theorem, which says that a necessary and sufficient condition for pro-representability is the vanishing of homology groups of the tangent complex in positive degree. Okay, so here's a very, very sketchy definition of the derived deformation functor. So, first I should say there's a couple ways. The couple ways they define it. One is they somehow cook up a projective system of simplicial sets associated to an étale homotopy type, whatever that means, of some ring of integers. And then there's also some functor associated to the group G. This functor is called BG. And then they define this derived deformation functor as a homotopy fiber of maps from XS to BG. And these functors are satisfy some properties that we're going to introduce today or explain today. Homotopy invariant, preserved homotopy pullback are formally cohesive, and so that's why I want to bring up this stuff here, is just to motivate why we're going to be talking about all these conditions essentially from homotopy theory. Okay, so now let's move on to homotopy colimits and homotopy limits. One reference for this section is Galatius and Venkatesh Appendix A. I also, unfortunately, I think I spent too much time preparing this part of the thing, so it's a little more than is probably necessary. Okay, so first let's ask, why do we need homotopy colimits? And one way they arise is that the ordinary colimits and limits in a model category are not homotopy invariant. In other words, if you have two diagrams, f and g, and you have a natural transformation so that natural transformation t, so that for each object or each index I, f of I and g of I are have a weak equivalence between them. So sometimes we say that t is a level-wise weak equivalence, and so it will be a weak equivalence in an appropriate model category structure on this functor category. Then the colimit of f and the colimit of g, the map induced by taking the colimit of t, might not be a weak equivalence. And here's a simple example in the category of topological spaces. So consider the Sn formed by gluing two hemispheres, dn along the equatorial Sn minus 1. So here's a dn up here, a dn up here, down there, and then Sn minus 1 along the equator. So the push out of a diagram that I just drew is Sn. Now what we can do is replace each of these dn's by a point, since they're contractible, and so we have a weak equivalence from dn to a point, and similarly dn to this point, but now when we take the push out or colimit, we just get a point, and so clearly Sn and a point are not homotopy equivalent. In other words, they're not a weak equivalence between them. So this illustrates the need for, or at least the point that ordinary colimits are not homotopy invariant. In other words, if you replace their objects by weak equivalence, you get a different, potentially different colimit. And in this example, a homotopy colimit is Sn. So I purposely crossed out the here because, as I'll explain I think on the next slide, the homotopy colimit is not defined up to unique isomorphism. Okay, so the ordinary colimit or limit, that's what my notation of co in parentheses means. So is a diagram, of a diagram is unique up to unique isomorphism, so it's common to say the colimit or the limit. However, the homotopy colimit is not defined up to unique isomorphisms, and there's several possible choices, or what's called models, for an object in a model category to be a homotopy colimit or limit of a diagram. The most important property of homotopy colimits is that if two diagrams f and g, and if we have a natural transformation t between them, so that at each level t induces a weak equivalence, then the induced map between the limit or colimits of f and g is a weak equivalence. So here's an example of a homotopy limit. So suppose we have a three-object category, and then we have this kind of pullback diagram, and then assume y takes values in complexes. We'll see that to give a map from an arbitrary simplicial set x to the homotopy fiber product consists of giving let's say 5 maps here that whose domains and targets are as indicated in this picture here. But this diagram does not commute, rather homotopy commutes, or commutes up to homotopy. In other words, okay, so there's at least 2 approaches to defining what a homotopy colimit or limit is, of a particular diagram. And okay, so one approach is the abstract homotopy theory approach via model categories or variants like infinity 1 categories. So put a model structure on the functor category and then take derived functors of the usual colimit or limit functor. And what this involves is you take f, take a cofibrant or fibrant replacement of it in this model category C to the I, and then take the ordinary limit or colimit of that functor, or diagram, I should say. Then the second approach is via explicit formulas, such as ones given in this book by Bussold and Kahn, in which we thicken, if necessary, each object and then take the usual colimit of the new diagram. Okay, so I'll explain both of them. And well, here's a quote I found from the source listed here. For many purposes, the abstract existence of homotopy limits is all you need, or colimits. However, there's also many cases where a concrete minimalistic realization of them is useful for working with abstract notions. So the point is both notions are useful. Okay, so the first approach is the abstract approach. Let C be a model category and I be a small index category. And then the various naive, by which I mean level-wise, classes of cofibrations, weak equivalents, and fibrations may not give rise to model structures in general. But if C is what's called a combinatorial model category, we won't really need to know the definition of it. But an example is that of simplicial sets with its standard model structure. Then the following 2 are indeed model structures on the functor category C to the I. One is a projective model structure where weak equivalents and fibrations are calculated component-wise. And then the second is the injective model structure where weak equivalents and cofibrations are calculated component-wise. So the abstract approach continued. All right, so suppose we have a combinatorial model category. Then we have a pair of equivalent adjunctions, the colimit and the constant functor that just gives rise to the constant diagram are equivalent adjunctions, and then the constant functor and the limit are also equivalent adjunctions. And then one way to define the homotopy colimit is you basically take the left-derived functor of the colimit, and what that means is you start with your diagram F, take a cofibrant replacement. Again, that's somewhat abstract. What exactly is this cofibrant replacement? And then once you have QF, that's new. This is new diagram. Then you take the ordinary colimit of QF. Okay, and then this functorial replacement map for cofibrant replacement goes from QF to F, and so when you take colimits, you get a map from the homotopy colimit to the ordinary colimit of a diagram F. And this need not be a weak equivalence, although it is a weak equivalence if C is filtered. Galatius and Venkatesh point out that sometimes, though, it's still useful to consider the homotopy colimit separately. And then there's a dual story for homotopy limits where you just switch the arrows, and then in this case you start with this diagram F, take the fibrant replacement, so the map goes from F to fibrant replacement RF, and then the induced map on limits goes from the ordinary limit to the homotopy limit. Okay, so that was the abstract approach. What are the explicit formulas? So they go through this in some detail in Galatius and Venkatesh actually. It turns out that, okay, so you start with some diagram X, and the homotopy colimit, it's first of all a simplicial set, and it has the following universal property, that to give a map out of it amounts to specifying maps of simplicial sets like so, where this here is the nerve of the category of objects underneath this lowercase I in a way that's compatible. So here I have one fi for one I, here I have fi prime for another index I primed, and the compatibility condition is that the following diagram commutes. So intuitively, okay, the original diagram was made out of these things. We've sort of thickened them a little bit by adding these nerves, and then what's going to happen is we just take the ordinary colimit of this new thickened diagram. Okay, so hence we see that to construct a specific simplicial set that models this homotopy colimit is to take the co-equalizer, this collection of simplicial sets, or this map of simplicial sets. This is just how you can think of, the ordinary colimit of sets is you just take their union and then mod out by some commutativity conditions. That's basically what's happening here. Okay. And we'll also recover the map from the homotopy colimit to the colimit by, if you send a nerve to just a point, there's a unique map that way, and then that gives rise to this map down here. It's are similar. So the homotopy limit of a diagram, so again it's a simplicial set with the universal property that maps to it from an arbitrary simplicial set X, amount to giving a map from X thickened by this nerve to each object Y, I, and with some compatibility conditions that make this diagram commute. And since we have this Hom tensor junction in simplicial sets, that diagram on the previous slide is equivalent to commutativity of this diagram, and then we can use this to express the homotopy limit as basically the ordinary limit of the objects in this type of diagram. And that's what this next line here says. The homotopy limit is the equalizer of this, all these simplicial sets. Okay, so let's move on to representable and pro-representable functors. This is sections 2 and 3. So two functors, f and g, from Artin local rings to simplicial sets. And we say that a natural transformation between them is a weak equivalence if it's a level-wise or component-wise weak equivalence. That means for each object, or K algebra A, f of A to g of A is a weak equivalence of simplicial sets. And then two functors are naturally weakly equivalent if there exists a finite zigzag of natural weak equivalences between them. So for example, any functor has a natural weak equivalence to a functor valued in Kahn complexes. There's actually a couple ways to do this. One is to use the singular functor. So what you do is take the simplicial set f of A, take its geometrical relation, and then take the singular simplices in there, and this is gives rise to a natural weak equivalence. So the set of singular simplices is huge. So there's a little bit smaller simplicial set that one can come up with. This is the second way, is something called Kahn's adjoint subdivision functor, and that's a functor from a simplicial set A to some other simplicial set, and just keep repeating that functor, and that's what x infinity is. And one advantage of this is it stays within simplicial sets, doesn't require passage to geometricalization, and in some sense it's smaller than the singular simplices. Secondly, a simplicial enrichment of a functor from Artin to simplicial sets is the specification of maps of simplicial sets from the Hom sets, the Hom simplicial sets in the Arndt category to the Hom simplicial sets of f of A and f of B in the simplicial category of simplicial sets, and it agrees with f on the zero simplices and compatible with composition. And when f is simplicially enriched, there's a Simplicial Yoneda lemma, which says that for R and Artin simplicial ring, there is a functorial bijection of sets between natural transformations, between the functor associated to R and any random functor f, that's simplicially enriched, of course, to the vertices or zero simplices of f evaluated at R. And the correspondence goes as follows. If you have a natural transformation T, the corresponding vertex you send it to is evaluate T at the identity vertex. Most functors we will be interested in will be homotopy invariant, which means that if A to B is a weak equivalence of Artin rings, then f of A to f of B is a weak equivalence. For any homotopy invariant functor, there exists a natural weak equivalence to f to f primed, where f primed is simplicially enriched and convalued. CG Galatius and Venkatesh for a proof, they give a relatively simple construction. So when proving a property about a homotopy invariant functor, and such a property that depends only on the natural weak equivalence class of the functor, we may assume f is simplically enriched and convalued. This will come up in the proof of Lurie's derived Schrödinger theorem. A functor on simplicial rings to simplicial sets is representable if it is naturally weakly equivalent, so potentially via some zigzags, to the functor given by Hom of R, Homs out of R, for some clobe-fibrant ring R. A representable functor is homotopy invariant, and here's the proof. So, since homotopy invariance is just a question about weak equivalences, we can assume that our functor equals the Homs out of R for some cofibrant R. And okay, as recalling the definition, we need to show that if A to B is a weak equivalence between simplicial rings, then the induced map between functors of maps out of R is a weak equivalence of simplicial sets. Ken Brown's lemma for model categories says that we can assume additionally that A to B is a trivial fibration, and then use that R is cofibrant and one of the lifting properties of cofibrations with respect to trivial fibrations. Okay, moving on to pro-representability. So in general, a pro-object of a category C is a functor R from J op to to C, where J is some small filtered category. And the definition of pro-representability is a functor is pro-representable if they're a object R from J op to Artin simplicial rings, indexed by some filtered category, and with all the R sub J cofibrant, such that F is naturally weakly equivalent. Recall that this means by a zigzag to the functor given by the colimit of Homs out of Rj. Any pro-representable functor is homotopy invariant, since we've seen that each individual functor that's representable is homotopy invariant, and then secondly, a filtered colimit of simplicial sets commutes with the homotopy groups. Here's an example of a pro-representable functor that's not representable. So recall that K is a field. Here we're going to need that K is a finite field, and so let P be its characteristic, and then again elements of R over K are rings R with maps to K. Okay, then this terminal functor we claim is pro-representable but not representable, and it's not representable because suppose it was represented by an Artin ring R, and let n be such that P of the n is equal to 0. So recall that the definition of Artin simplicial ring, the pi 0 of the ring R is an Artin local in the usual sense, and so and P is in the maximal ideal of it, and so P to some power is going to equal 0 in pi naught of R. And then, okay, choose some ring A such that P of the n is not 0. For example, the width vector is mod P of the n. And then Homs from R to A, there's none, since P of the n is 0 in R but not in A. And the empty set is not equivalent to the singleton set. Okay, to show that the singleton or terminal functor is pro-representable, let Rn be the ring obtained by freely adjoining to the discrete simplicial ring Z, a generator Y in degree 1 from 0 to Pn. Note that P times Y is the edge or one simplex from 0 to P of the n plus 1. This Rn is a cofibrant approximation to the width vectors in K mod P of the n. And we have these maps from Rn plus 1 to Rn. And then F is pro-represented by this projective system. The details, which I've skipped over, are in Galatius-Venkatesh, proposition 3.4. Now, let's go back to homotopy pullbacks and recall that it's well defined up to weak equivalence, but not up to isomorphism. And in any case, regardless of the definition, the model we choose, the following definition makes sense. So we say that a commutative diagram in simplicial sets is a homotopy pullback square, or homotopy Cartesian, if the composite map from Y to the homotopy pullback is a weak equivalence. So let F be a homotopy invariant functor. We say that F preserves homotopy pullback if for every strictly Cartesian diagram A to ABCD in R with B to D surjective in simplicial degree, if we apply F, we get a homotopy Cartesian diagram. And again, by homotopy Cartesian, that just means that the natural map from f of a through the strict fiber product to the homotopy fiber product is a weak equivalence of simplicial sets. An easy fact is that a map of simplicial rings, beta d, is surjective in all simplicial degrees if and only if it is a fibration and induces a surjection in pi 0. If we have a strict fibrous square of Artin rings, then since beta d is a fibration between fibrant objects, the strict Cartesian fiber B cross C over D is a model for a homotopy fiber. Some more definitions associated with functors are the following. So a functor from Artin simplicial rings to simplicial sets is reduced if f of k is contractible, and we say it's non-reduced otherwise. A functor is formally cohesive if its homotopy invariant preserves homotopy pullback and is reduced. So why are we interested in formally cohesive functors? Recall it's called the classical version of Schlesinger's theorem. Let discrete Artin be the category of ordinary Artin local rings together with a map to K. Schlesinger's theorem says that if you have a functor on discrete Artin rings to sets, then, and for every fiber square diagram of Artin local rings, if we want to consider this canonical map between the strict fiber product and f applied to the strict fiber product and the strict fiber product of f applied to the components of the square. Schlesinger's theorem says that, well, if there's a bunch of hypotheses that are satisfied on this map labeled with asterisk, then the functor is representable. So on the next page, I have listed what these conditions are. So, for example, if this map star is surjection whenever we've got a small extension, and a bijection when we've got a specific extension over here, and a bijection in some other case. So this is kind of where the motivation may be for this idea of formally cohesive functor. Remember, that's where an analogous map, a map that's analogous to star, is a weak equivalence. Now, representable functors are, well, they're not quite formally cohesive, but they almost are. So suppose we consider the functor of Homs out of a cofibrant ring R, and it's homotopy invariant, and it preserves homotopy pullback. Why? Well, we have to check the following. So we start off with a strict Cartesian diagram, apply the Homs out of R functor, we get this other diagram, and since beta d is a fibration, Homs out of R applied to beta d turns out also to be a fibration, and that's because R is cofibrant. A lifting argument applies there. And then, hence, when you have a fibration and you want to take or compute the homotopy pullback, it turns out that agrees with the strict pullback. However, Homs out of R need not be reduced, and so a representable functor need not be formally cohesive. Formally cohesive is going to be one of the hypotheses in Lurie's derived Schlesinger condition. So we'd be interested in ways of how to fix a non-reduced functor or adjust it to become reduced. So in general, the number theory applications in Galatius and Venkatesh, the Galois deformation functors initially will not be reduced, and there are ways to proceed to make it reduced. So one way is you pick a zero simplex x in f evaluated at k, and then consider the homotopy fiber f of x, f sub x I should say, over x. And this will be a formally cohesive functor. I'll say more about that on the next slide. That's one thing you can do. Or the second thing is you can replace the target category of simplicial sets by simplicial sets with maps to z, where z is f of k. And so f of k is terminal, but we'll need to additionally assume that it's homotopy terminal in order to get a reduced functor f on Artin simplicial rings to simplicial sets with maps to z. The following simple construction shows how to modify a homotopy pullback preserving functor to get a reduced and hence formally cohesive functor. You take a zero simplex in f of k and take essentially the fiber over it. And so this will give a reduced, or in fact, formally cohesive functor. And this idea will come up later when we make local systems of functors f sub sigma as you vary sigma over the simplices of f of k. Here we've just chosen one specific zero simplex, but we're later going to, I mean not in this talk, but later in the paper, we're going to consider all of these sigma range over the simplices of f of k. This is somewhat of a random fact here. Homotopy limits of formally cohesive functors are formally cohesive. That's essentially what the slide is saying. So for example, if we take the homotopy fiber product of three formally cohesive functors, we get a formally cohesive functor. Okay, now we can finally get to the main topic of this talk, and that's the tangent complex of a formally cohesive functor. And this is Galatius and Venkatesh section 4. So what are we aiming for? So we start with a formally cohesive functor, and we're aiming to build a chain complex of k vector spaces, and it will possibly be unbounded in both directions. And let's recall the strategy again. So Galatius and Venkatesh write, it seems difficult to directly define a chain complex Tf from a formally cohesive functor f. Instead, we construct an essentially equivalent incarnation of it as a spectrum with the structure of a modular spectrum over the Eilenberg-MacLane spectrum, HK. Then they use, so I guess that's the end quote, and then they'll use the Dole-Kahn correspondence, which provides a bridge between spectra and chain complex. So again, we start with the formally cohesive functor here, and in the next slide, I'll show you how to get to down here. Now Dole-Kahn is an equivalence, and so we can get to there. Now, I won't actually explain how to get to the HK module spectrum, but I'll say a few words later about why Galatius and Venkatesh go to it. Okay, so first of all, introducing the definition of a spectrum. The plural is spectra, and it's a definition arising in algebraic topology, especially used in stable homotopy theory. And there's many variants. Galatius and Venkatesh start with the most elementary version. And so a spectrum is a sequence of simplicial sets, base simplicial sets. That just means we have maps from a point to each En. And then, okay, we also have the data of maps from En to the loop space. of the next simplicial set in the sequence. Now recall from earlier that on simplicial sets there's a functorial fibrant replacement. There were a couple we saw earlier. Here we're going to use the con-adjoint subdivision functor. And then finally, a spectrum is an omega spectrum if, when you do the composite of these maps here, you get a weak equivalence. A spectrum has a homotopy groups, and these are defined as follows. For any integer k, possibly negative, the definition is you take the co-limit of pi n sub k of the nth space, and you let n go to infinity. Here's what the maps from the n plus k homotopy group of En to the n plus k plus 1 homotopy group of En plus 1 are. So a homotopy group is the homotopy classes of maps from the sphere to En. Then you apply the suspension functor. The suspension of a sphere is a sphere one-dimensional higher, and then we get a map from the suspension of En to En plus 1 by taking the adjoint map to this map that comes along, epsilon n, that comes along as part of the data of a spectrum. Okay, so now let's go back to our formally cohesive functor f, and just like in the classical tangent space of a functor on discrete Artin rings to sets, it's defined by evaluating f at the specific Artin ring k epsilon. What we're going to do is take our strictly cohesive functor f on Artin simplicial rings and evaluate them at a whole bunch of Artin rings of this specific form, k plus the square zero extension of this module k shifted by n. So we're going to recall what these modules and rings are in the next few slides. All right, so for a simplicial k module v, let k O plus v be the simplicial ring defined by the square zero extension in each degree. This comes with obvious map to k. And it might not be an Artin ring, but it will be if there's some finite condition on the homotopy groups of v. Then let k adjoin n be the free simplicial k module generated by the pointed simplicial set Sn, which as a simplicial set is you take the n simplex and mod out by the boundary. And one fact about its homotopy groups are that they're in degree n only and 0 otherwise. Now, an alternative way to construct the simplicial module k brackets n is to apply the Dold-Kahn functor that we're going to talk about next to the, or later, to the suspension or shift of just a single k, and the suspension is just the chain complex with k in homological degree n and zeros elsewhere. Okay, so then ko plus k brackets n is a square zero extension, and to motivate the analogy with the classical setting, note that k plus k0 is isomorphic to the ring of dual numbers. We're going to define k brackets tilde as follows. We factor the 0 map from 0 to k brackets n into a weak equivalence followed by a fibration. We could in fact have a trivial cofibration followed by fibration, but okay. And note that brackets kn tilde is a model for the homotopy fiber product. Okay. Now, one thing I didn't understand, but okay, is we have a strict pullback square over here. And fine, what we're going to do is, let's assume that we have this here. And we're going to apply a formally cohesive functor f to it, and formally cohesive turns strict pullbacks to homotopy pullbacks, so we get this homotopy pullback square. I've unfortunately I forgot the f's here. And so we have weak equivalences by definition of a homotopy pullback square as shown. And if we work through these weak equivalences, the point is we get the condition to be in to be a spectrum. We need to map from f to omega, or loops on another, the next set in the simplicial set in the spectrum. Okay, so finally we can define, what I'm calling the tangent spectrum. And this is, Galatius and Venkatesh call it the tangent complex. I mean, they call two different things a tangent complex. So to distinguish them, I want to call this a tangent spectrum. So we start off with the formally cohesive functor. And suppose for some reason it's convalued. If it's not, you probably have to do fiber replacement. But anyway, okay. So then the tangent omega spectrum is given by you take f and evaluate it at these special art and simplicial rings, and then the structure maps are what the last slide was trying to motivate, essentially. So we have explained the arrow, going from here to here. Next, we're going to explain this arrow. So the classical Dold correspondence is from bounded, so that's what the plus means, non-negatively graded chain complexes of k-vector spaces to the category of simplicial k-modules. Galatius and Venkatesh extend it to unbounded chain complexes as the domain, and then the target as omega spectra. The inverse functor n for normalized chain complexes is actually a little bit easier to define, so let me define that first. So that takes a simplicial k-module A, and I have to give back a non-negatively graded chain complex of k-vector spaces. And here's the definition. The nth term of the chain complex is given by the kernel of these maps. All the face maps except for D0, and then the differential is just given by D0. Intuitively, the k-module or k-vector space NA sub n consists of the n simplices of A, so it starts out with the elements of AN, whose boundary faces are 0, except for the face opposite the initial vertex of the simplex. So an element that's in the kernel of the map from degree n to degree n minus 1 in the chain complex will be an n simplex of AN whose boundary faces are all 0. So in other words, it will look like an S to Sn. So then Conversely, the Dole-Kahn map itself, so given a non-negatively graded complex of K vector spaces, the simplicial abelian group in degree n is given by this formula here. So it's a bunch of copies of the terms, the lower degree terms in the vectors, in the chain complex of K vector spaces, and terms of degree n or lower. And then here's the behavior on maps in the simplex category. Basically, you have to, given m to n in the simplex category, factor it into a surjection followed by an injection, and then map VL to VS, where D is the differential in the chain complex. So intuitively, the elements in the K-vector space Cn give rise to non-degenerate simplices appearing in the degree n simplicial module Dole-Kahn of C, indexed by the summand of the identity map. One important factor of Dole-Kahn is that it preserves the homotopy / homology groups. In other words, you start with your chain complex, and its homology in degree n equals the homotopy group of the degree n homotopy group of the Dole-Kahn simplicial K module. So far we've defined Dole-Kahn as a functor to simplicial sets, and here's how to turn it into spectra. So we start with first a general piece of terminology. If C is in a chain complex, possibly unbounded, then the shifted chain complex is denoted sigma C, and basically it's shift to the left is one way to think about it. Shift all the terms one unit to the left. For a bounded chain complex or non-negatively graded chain complex, we have a canonical weak equivalence between the Dole-Kahn of C to the loop space of the Dole-Kahn of the suspension of C, or shift of C. And that arises from the fact that when you shift a complex, the homology groups are shifted. And so the sequence of confibrant simplicial sets given by Dole-Kahn applied to successive shifts of C is an omega spectrum. So extending Dole-Kahn to unbounded chain complex is as follows. So you start with an unbounded chain complex, and then you can take the soft truncation, tau greater than 0, greater than or equal to 0 of C, as follows. So in degree 0, you replace C0 by the kernel of the C0 to C -1 map, and then everywhere else, in positive degree anyway, the truncated complex is the original complex. Negative degrees, of course, it's 0. Then applying Dole-Kahn to your truncated complex, specifically to, or truncated shifts of your complex, gives, as before, a weak equivalence of base simplicial sets. And then this allows us to define the Dole-Kahn functor on unbounded chain complex to omega spectra by sending an unbounded chain complex to the spectrum given by applying the Dole-Kahn functor to truncations of shifts of C. And then the data of the weak equivalences is this map given here. and the homotopy groups of the spectrum are canonically isomorphic to the homotopy groups of C. So let's look at the picture that describes the strategy. We've basically explained this map from unbounded chain complexes to omega spectra. Now, the original picture that I gave had us landing in something called HK module spectra. And what Galatius and Venkatesh say that this Dolkan functor from unbounded chain complex to omega spectra, so that's the one we've described so far, is a forgetful functor. It remembers enough about the chain complex to recover its homology groups via the homotopy groups of the spectrum, and in particular it detects quasi-isomorphisms, but it does not remember enough information to recover K-module structure on these homology groups. So in other words, the homotopy groups pi n of Dolkan of C don't see the K-module structure that's on these homology groups. We only have that the two groups are isomorphic as abelian groups. And so to recover this K-module structure on the homotopy groups, we need to put some type of K-module structure on the spectrum Dolkan of C. The incarnation of any ring R in the category of omega spectra is the Eilenberg-MacLane spectrum, HR, and that consists of a sequence of spaces called the Eilenberg-MacLane spaces, and these spaces represent the functor on topological spaces given by singular cohomology with coefficients in R. In other words, if you have a topological space X and you want to take its singular cohomology with coefficients in R, that equals the group of homotopy classes of maps from X to the Eilenberg-MacLane space KRN. Suppose we have an omega spectrum X using the intuition that a spectrum is a topologous abelian group, and then a K-module is an abelian group A along with a map from the tensor product of K and A to A satisfying the usual conditions. Some sort of K-module structure on a spectrum would mean a map of spectra from the spectral version of the field K, in other words, the Eilenberg-MacLane spectrum associated to K, tensor it in some sense with the spectrum X, and then a map from that tensor product to X. This tensor product is typically called smash product of spectra. So smash product of spectra are a long story, so defining a reasonable notion of smash product on the level of spectra is quite thorny and technical, and it led to the introduction of other notions of spectra, namely spectra associated to gamma spaces, symmetric spectra, orthogonal spectra, S modules. Galatius and Venkatesh mention a survey from 2001 that explains the relations between all these different types of spectra. And they explain it in some detail, Galatius and Venkatesh do, the Seagal's gamma spaces and the category of spectra valued in gamma spaces. This category has a smash product, and hence we can define the category of HK module spectra. Let's take this as a black box. Then the Dolkan functor that we've talked about from chain complexes to omega spectra constructed above or on a few slides ago naturally takes values in HK module spectra. So I'm not going to explain what HK module spectra are, but there's some sense of a K module structure on spectra. And let's switch gears a little bit and talk about cohomology of rings. So if B to K is a map of ordinary rings, then we have a natural bijection of sets from B to the dual numbers. So these are homomorphisms of algebras with maps to K, and that's isomorphic to the set of derivations from B to K, and that's isomorphic to the homomorphisms of B modules from the Kähler differentials of B to K. And then if we extend this level-wise to the simplicial setting as follows. Let R be an Artin simplicial ring with that's cofibrant. Then we have a natural isomorphism of simplicial sets, Hom from the simplicial ring R to this higher dimensional analog of dual numbers, and that's isomorphic to the homomorphisms of simplicial R modules from the Kähler differentials to K brackets n. K brackets n is made into an R module via the structure map of R to K. So for R in an Artin simplicial ring, let R to the C be its cofibrant replacement, and then define these homotopy groups pi negative n of TR as pi naught of the Homs from the cofibrant replacement of R to K O plus K brackets n, and using the equivalence on, or isomorphism on the previous slide, that's the same as pi 0 of a Hom in the category of simplicial R modules. And then we can similarly define the homotopy groups of a pro-object as the co-limit of the homotopy groups of the objects, making up the pro-object. And as we're going to explain, this pi negative n TR is going to be identified with the Andre-Killen cohomology of a map Z to R with coefficients in K. So right now, TR is just notation, but we're going to relate it to the tangent complex associated to the functor given by R. And then we'll see that pi negative n is the homotopy group of that spectrum. So that's what we're going to do next. So let R be a simplicial commutative ring. It doesn't have to be Artin, but it does have to have a map from R to K, and that will make the associated functor of maps out of R a reduced functor. So f sub R is the functor that R, or functor represented by R. And then the question we want to address is, what is the tangent complex of this functor? And I'll say the answer on this slide and explain a little bit on the next slide. So the answer is that the tangent complex, it's quasi-isomorphic to a particular chain complex, namely Hom of Dold-Kahn of the simplicial R module, that's the cotangent complex. You tensor that with K, and then you basically take the dual of this. Now this is the answer that Galatius and Venkatesh write out in their paper. I'm not sure I completely follow it, but I'll explain what I can understand. Now the homotopy groups of this tangent complex, or tangent spectrum, associated to this functor fr are the Andre-Killen cohomology groups of R with coefficients in K. And so in particular, the homotopy groups in positive degree, they vanish. And this is foreshadowing Lurie's derived Schlesinger. So let's review what the Andre-Killen cohomology is. If you have a map A to B of simplicial commutative rings, for example, a map of discrete rings, and then if you have a B module M, I think the B module has to be constant, although that wasn't mentioned in Galatius and Venkatesh. So if A to B is cofibrant, the Andrei-Killian cohomology groups, denoted like so, the ith cohomology of B with coefficients in M is the cohomology of the total chain complex associated to the co-simplicial abelian group given by the derivations of Bn to M that are an linear. And so basically it's the level-wise a-linear derivations of B taking values in M. This group of derivations, as usual, is isomorphic to the homomorphisms in the category of B n modules of maps from the Kähler differentials to M. Now the cotangent complex is the total chain complex associated to the simplicial B module of Kähler differentials of a simplicial resolution of B by free A algebras. And then a fact is that this cotangent complex can compute the Andrei-Killian cohomology by taking the complex that's the Hom of the cotangent complex into M, and then taking the cohomology of that complex. So Galatius and Venkatesh claim that the homotopy groups of this tangent spectrum of Fr are isomorphic to the Andrei-Killian cohomology. And they say it's because the tangent complex of Fr is quasi-isomorphic to this particular complex, explained a few slides ago, or mentioned a few slides ago. And I couldn't quite follow that, but here's my somewhat justification. So the homotopy group of a spectrum, by definition, it's the co-limit over J of the homotopy groups of various spaces appearing in the spectrum. If we take J equal to I, then that co-limit contains the pi naught of the ith space in the tangent spectrum. The definition of the tangent spectrum is you evaluate the functor at this Artin simplicial ring for our functor Fr, that's just Homs out of R. Then using the property of Kähler differentials, that's Homs of SR modules out of the Kähler differentials, and then that's isomorphic to the Andrei-Killian cohomology. So now we come to Leary's derived Schlessinger's theorem. And here's what it says. So suppose we have a formally cohesive functor on Artin simplicial rings. This notation here, throughout the talk I have not been using this S here. Okay, anyways. So this functor F is pro-representable if and only if the ith homology groups of the tangent complex vanishes for I greater than 0. And a technical addendum is that if the k-vector spaces that form the homology groups have countable dimension, then the pro-representing object may be chosen to have countable indexing category. So here's a partial sketch of a proof of Leary's derived Schlesinger. Now the easy direction is to assume F is pro-representable and say by a pro-object R, and then what we need to show is that the associated tangent complex, or rather tangent spectrum, T of the functor that's the co-limit of all the Homs out of Rj is co-connective. Now, as we've just seen, the tangent complex of any representable functor is co-connective. Then the tangent complex operation from functors to spectra takes filtered homotopy colimits of functors to filtered homotopy colimits of spectra. And so in particular, we have this relation down here. So another claim is that filtered colimits of co-connective spectra remain co-connective. And so in particular, the tangent complex of any pro-representable functor is co-connective. The hard direction, which I didn't fully understand, but let's just say what it is, it kind of follows the proof of the classical Schlesinger criterion by gradually building up the representing or pro-representing object. Okay, so conversely, suppose we have a functor on our simplicial rings that is co-connective. In other words, the homotopy groups of the spectrum vanish for I greater than 0. So Galatius and Venkatesh, or Lurie, build a projective system of simplicial rings, simplicial Artin rings, I should say, and natural weak equivalence between the homotopy colimit of those functors, those representable functors, to our original functor f. Without loss of generality, we may assume that f from Artin K to simplicial sets is a simplicially enriched functor that takes values in complexes. And the construction is by a transfinite recipe, recursive recipe, providing an improvement to any pair R, iota consisting of a fibrant Artin ring and a zero simplex in f of R. Then the Simplicial Yoneda, which holds because f is a simplicial enriched functor, gives a natural transformation between the functor of maps out of R to our functor f. And this is where I'm going to actually stop. I didn't quite fully understand the proof, unfortunately. I might make a separate video where I do. Perhaps it's good to end on a cliffhanger anyways. So thanks for watching. I tried to explain as best I could what I could understand. And if you have any questions, email me or leave them in the comments below. Thanks again.